Okay, here is the demo for lesson 5.1. Our work in chapter 3 has allowed us to understand linear systems completely. Unfortunately, nonlinear systems aren't quite as nice, and our main technique in studying the solutions of linear systems will be to find equilibrium points and linearize the system around them. So linearization is something you studied in Calculus 1 and Calculus 2. We're going to be doing it a little bit more in depth now. And once we linearize around an equilibrium point, then we know the behavior of the system near the equilibrium points, and we can maybe guess at the behavior between them. Okay, so here is a nonlinear system, and I want to find all the equilibrium points of the system. So equilibrium points are the places where x prime and y prime both equal 0. So I want to set x prime equal to 0 and y prime equal to 0. Okay, so x prime is just y, and y prime is negative y minus sine x. Okay, so I know y equals 0 is the y component of each of my equilibrium points. So in my other equation, I'm going to replace the y with a 0, and I just get negative sine x equals 0. And the negative doesn't matter, sine of x equals 0. And that happens at positive and negative multiples of integer multiples of pi. So plus or minus n pi for every n in the integers. So that would be plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. Okay, so here's a direction field with a phase portrait sketched on top of it. This is a global view. So you can see several equilibrium points. This is 2 pi, pi, 0, negative pi, and negative 2 pi. And then if we zoom in on the 0, 0 equilibrium point, it looks very much like a classic spiral sink. So there isn't any weird nonlinear behavior in this picture like there is up here. This is very complicated behavior. This looks like a spiral sink that we have learned how to analyze before in chapter 3. There we go. Yes, this is spiraling in towards the origin in a clockwise direction. We can verify this local behavior around the origin analytically by approximating the system with another system that's much easier to analyze. Our original system is x prime equals y, and y prime equals negative y minus sine x. So let's suppose we want to study the behavior of the system near the equilibrium point 0, 0. So the sine x term is the only nonlinear term in the system. Y and negative y are both linear. So the sine of x is nonlinear, so we're going to use an old trick from calculus to replace sine of x with a polynomial. We'll use its Taylor series. We all remember that that is the Taylor series expansion for sine of x. So my new system is going to be x prime equals y prime equals negative y minus, instead of sine x, I'm going to put the Taylor series, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, dot, dot. Okay. So in this system, we want to circle all the nonlinear terms. So that would be this one and all the other terms in the Taylor series, except for the x. So now we're just going to drop the higher order terms in order to obtain the linearized system. So we get x prime equals y, and y prime equals negative y minus x. And now we can analyze this linear system using the techniques of chapter 3. So that means find the eigenvalues and determine the type of behavior at the fixed point 0, 0. Okay, so we have x prime, y prime. equals something times xy. So what has to go in this matrix? It would have to be 0, 1. That would give me 0x plus y. And then negative 1, negative 1. And then I'm going to take the determinant of a minus lambda I, this is a, and set it equal to 0. So the determinant of negative lambda 1, negative 1, negative 1 minus lambda, that is going to be negative lambda times negative 1 minus lambda minus negative 1. Set that equal to 0. That gives me lambda plus lambda squared plus 1 equals 0. And I'm going to use the quadratic formula on this. So lambda is going to be negative 1 plus or minus the square root of 1 minus 4 times 1 all over 2 times 1. So this is negative 1 plus or minus 1 minus 4 is negative 3. So this is the square root of 3i all over 2. So we have a complex eigenvalue with a negative real part. That means this is a spiral. It's a spiral because it's complex, and it's a spiral sink because the real part is negative. Slide. Okay, so to sketch it, I might draw 1 or 2 little arrows. I know that this is going to be a spiral sink, so I might choose, one spot here and just see what that arrow looks like in the direction field. So remember, my system was x prime, y prime equals 0, 1, negative 1, negative 1, and then I'm going to plug in this point, which is about half of pi over 2 is like, I don't know, 0.7, 0.5, something like that. Okay, so when we multiply that out, 0 times 0.7 plus 1 times 0.5 is 0.5. And then negative 1 times 0.7 plus negative 1 times 0.5 is negative 1.2. So that points left and down. I'm sorry, right and down. It's positive 0.5. So right and down, kind of like that. So this must be spiraling in like that. Let's see, does that jive with what we had on the previous slide? Okay, so this is the direction field and phase portrait for the nonlinear system zoomed in at the equilibrium pi, 0. This looks like a saddle. It looks like I've got some straight line solutions here, and then these classic saddle bits. So doing a linearization on an equilibrium point other than 0, 0 is trickier than the just drop the higher order terms. Since x and y are not very, very small, you can't just throw away the higher order terms. Being able to throw away the higher order terms is rooted in the fact that when you square something very, very small, it gets very, 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 very small. So it's like a lot smaller and you can throw that term away. That's not true when you're not near 0. But luckily there is a shorter process to linearize a nonlinear system. It can be used for any equilibrium point. If we have x prime and y prime equaling functions of x and y, and x naught, y naught is an equilibrium point, if you want to understand the behavior of the solution near x naught, y naught, we're going to linearize the system by calculating the Jacobian matrix of partial derivatives. So the partial of f with respect to x and the partial of f with respect to y, then the partial of g with respect to x and the partial of g with respect to y. You plug the equilibrium point x naught, y naught into the partial derivatives, And that is the coefficient matrix for the linearized system. Okay, so we're going to use this method to analyze the behavior of the system at pi, 0 and negative pi, 0. So the Jacobian matrix, which we call J for short, is the partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, and the partial of g with respect to y. This is f, and this is g. Okay, so the partial of f with respect to x. So when you're taking a partial derivative with respect to x, any other variable you see, you treat like a constant. So this y, you treat it like a constant, its derivative would be 0. And then when I take the partial with respect to y, you treat y as though it's the variable, and the derivative of y would be 1. And then the partial of g with respect to x, so I'm looking at this bit. This term has no x's in it, so we just treat it like it's a constant. Its derivative is 0. And then the derivative of sine of x is going to be cosine x. So I get negative cosine x. And then I take the partial with respect to y. So the derivative of negative y is negative 1. And the derivative of sine x is 0 because there's no y's in there, so we treat it like a constant. Then I'm going to plug in pi and negative pi. So I need to know the Jacobian at pi, 0. So plugging in pi for x and 0 for y, there aren't any y's in this Jacobian matrix, but if there were, I would make them zeros. So I get 0, 1, negative 1. And then the cosine of pi is negative 1, and I already have a negative here, so that becomes positive 1. And then the Jacobian at negative pi, 0, is going to be 0, 1, negative 1. And then I plug negative pi in, and that is also, the cosine of negative pi is negative 1, and there's a negative in front, so it's 1. So we get the same linearized matrix for both pi 0 and negative pi 0. And if I want to sketch their phase portraits, I need to find the eigenvalues. So I'm going to do the determinant of a minus lambda I. So that's going to give me negative lambda 1, 1, negative 1 minus lambda. So that's going to be lambda squared plus lambda plus minus 1. Set that equal to 0 and solve for lambda. So I'm going to get lambda is negative 1 plus or minus square root of 5 over 2. So that's two distinct real eigenvalues. One's positive, one's negative, so I'm going to get a saddle. I'm going to get the same eigenvalues for this one. And I'm just going to get approximate values for this because it'll be handy to have them. And we get 0.62 and negative 1.62. I would need eigenvectors to sketch in the straight line solutions. So my eigenvectors, remember you get those by solving a v equals lambda v for each lambda. So a is 0, 1, 1, negative 1 times xy equals 0.62 times xy. So y equals 0.62x, and I'm just going to plug in any x value like 1, 0.62. So 1 would be somewhere over here, 0.62 is like that, so but this is my equilibrium point, so I'm going to treat this like the origin. So from pi to 3 pi over 2, that's pi over 2, which is about 1.5. So 1 would be like right there. And then 0.62, that would be like right here. So I'm going to use this as my straight line solution. And that was my positive eigenvalue, so these are pointing away from the origin. And then I have to do a similar AV equals lambda v calculation for negative 1.62. And I'm going to get y equals negative 1.62 x. So if I make x1 again, negative 1.62 would be like here. So this is my other straight line solution, and it's the negative eigenvalue, so it points in, and then my saddle pieces look like this. And then this equilibrium point is going to look exactly the same as the one at pi, because it has the same Jacobian matrix. So if I want to try to stitch together the entire phase portrait, I have little bits. I know that at pi comma 0, I have something that looks like a saddle. This one was out, this one was in, and I've got like that, and like that. And I know that at 0, 0, I have a spiral sink that's rotating clockwise. So something like this. That wasn't good. And then at negative pi 0, I have a similar saddle to what I have at pi 0. These are in, this is out. So that's what I know. I know little tiny pictures at near the equilibrium points, and then I'm going to try to sort of stitch them together. So I'm guessing that this straight line solution, at some point, it's going to get close enough to this spiral sink that it will get captured and pulled in to the spiral sink like that. And then the same thing with these saddles. These saddles will get captured and pulled in. And then this straight line part of the saddle could also get captured and pulled in. I think I'm going to change the color. So it's eventually going to get close enough to this spiral sink that it gets pulled in there. These saddle pieces will get pulled in. And then over here, these are going to head over towards another spiral sink like that. And we're going to get the original nonlinear phase portrait that we saw on the first slide.